lecture we have discussed about the basic concepts of radioisotope technique. If you could recall, we have discussed about the nature of radioactivity, where we have discussed about the atomic stability. Now, if you as in atomic stability, the ratio of the neutrons to protons determines, and with various nuclear forces determines whether a nucleus will be stable or it will be unstable. Now, when it is unstable, then that nucleus is bound to emit either radiation or matter or both to become stable, and in this process it might change its characteristic, that is, an element can change from one form to another, and the process is known as transmutation. Now, this decay could be occurring for several reasons. One, there could be a neutron to proton ratio could be high, or neutron to proton ratio may be too low, and other factors. Now, this decay, which is in terms of electromagnetic radiation or subatomic particles, can happen through various ways. Like for example, like we have discussed earlier, the decay could happen by the emission of a positively charged or negatively charged beta particle, which is called negatron, which is negatively charged, and positron, which is positively charged. It could occur by heavier nuclei, which is called alpha particle or helium nucleus, or it could occur by a simple electromagnetic radiation, which is gamma rays, and in one case we have discussed electron capture, where X-rays are generated. So, there could be different ways where a radioisotope can decay. Now, in this lecture we will further take our discussion and understand other concepts in this radioisotope techniques. Now, if you could recall, we ended the discussion in the last lecture, we were discussing about decay energy, and so now we will start with decay energy and units of radioactivity. Now, decay energy, like I said, they are mostly expressed in terms of electron volt, but 1 electron volt is not a large enough energy, and so the majority of isotopes, the term million or mega electron volt is more applicable. Now, if you compare different emitters like alpha emission emitter particle or beta particle or gamma radiations, their energies have a particular characteristics. For example, alpha particles or alpha emitters have a decay energy in the range of 4 to 8 million electron volt, while beta and gamma emitters in general have decay energy less than 3 million electron volt. Now, let us little bit go more into beta and gamma. Now, gamma also have a range where it is up from 10,000 electron volt to 10 million electron volt, but for beta emitters there is a range of energy, and this particular range of energy is called beta spectrum, because you have from very low energy, that is a continuous range from very low energy to very high energy, the beta particles are emitted, and this is, if you plot it, this is a relative probability of emission of a beta particle as a function of energy, then it is called a beta spectrum. Let me show you this on your screens, that how different beta particles or beta emitters have a range of energy where beta particles are emitted. Now, let us take a few examples here, where we can see the energy spectrum of negatron emission. Now, for example, if I draw this for a few of those negatron emitters, now this specifies n is the number of atoms with a particular energy E, and this is energy in terms of million electron volt. So, if I just plot, for example, as you will see, then if I am plotting for H, that is 3H, then this the plot looks something, it is a very approximate plot. So, you have to understand that it will look something like this actually, where this will be E maximum and which comes around 0.018 million electron volt. Now, remember here number of atoms with that particular energy are very less or almost none, and here number of atoms with low energy they are very high. So, we take somewhere around a mean, that is number of atoms with a mean energy, and that comes around 0.0055 million electron volt. So, this is like you can see the beta spectrum for 3H. Now, if we compare this to others, like for example, let us see for another beta emitter, that is a medium energy beta emitter 14C, and these axes will be same as we have drawn here, that is Ne, a number of atoms particular energy, and energy in terms of million electron volt. Then it will be somewhere, it will also show a particular characteristic pattern. Now, here it is having little higher energy because 3H is a weak emitter, but your what you call 14C is a medium energy emitter, and this particular here, if you see the E maximum is around 0.156, this E maximum here is around 0.156 million electron volt, and E mean, if I have to say, that is around 0.05 million electron volt. It is higher than the 3H, but there is a spectrum here, and where you will find that less and less number of atoms are at high energy, and so you can have a mean value. One more example I can take here, and that is of particular one which is 32P. I think all of you are aware about it. So, it is you can say strong emitter, and this has higher energy of particles. So, if I say this, it has a higher energy and it is rather different one. Now, here E maximum here is almost 1.71 and E mean is somewhere around 0.70. So, you can see the beta spectrum here, that they are being emitted at from 0 to a maximum energy, and so this is a characteristic feature of only negatron emitters and not the alpha or the gamma radiations. Actually, they have a particular range. So, I hope you have been able to understand that what we mean when we say beta spectrum in here. All right. So, let us move on now. All right. So, this was like how a particular beta emitters emits particles in a continuous range of energy from 0 to a maximum value, and we take E mean for these particles, which is near the mean energy, and it is roughly 1/3 of E max. All right. So, as we have seen in the graph or spectrum, the particles with E max are very less, and particles somewhere in between are taken as the number. All right. Now, how this radioactivity in terms of units is expressed? Let us see that. Now, in international system of units, that is SI systems, the units of radioactivity is becquerel, in honor of the scientist Henry Becquerel. Now, 1 becquerel is defined as 1 transformation or disintegration per second, and it is mostly expressed in terms of gigabecquerel, that is 1 into 10 raised to power 9 decay per second, or terabecquerel, that is 1 into 10 raised to power 12 decays per second, and is commonly used. These are most commonly used. Now, there is another widely used unit which is curie. based on Madam Curie's name, and this is expressed as Ci. Now, 1 Ci or 1 Curie is defined as number of disintegrations per second per gram of radium, and it equals 3.7 into 10 raised to power 10, 10 raised to power 10 disintegrations per second, or we can say 37 gigabecquerel. Now, for most biological applications, the unit is too large and microcurie or millicurie is used rather than simply the curie. So, for practical purposes, it is not possible to detect actual number of disintegrations. So, we have to keep in mind when we are detecting, and as we will discuss in coming lectures, this is very difficult to capture or to record actual number of disintegrations taking place. So, what you really count is the number of radiations you have counted, and it depends on efficiency of counting, that how many particular events, radioactive events you can count. Now, therefore, radioactivity is generally stated as detection or detected counts per second. For example, it could be CPS or it could be counts per minute. For a particular quantitative experiments where you require absolute amount of radioactive material to be calculated, then this value, that is counts per minute or counts per second, needs to be converted into disintegration per minute or disintegration per second. This is done by dividing by the efficiency of counting. So, that is a method to determine absolute counting. Now, in most experiments, radioisotopes are rarely pure actually. That means, a carrier of the stable isotope of the element is added in here for stability and other factors. Therefore, the amount of radioisotope present is expressed in terms of a specific activity, that is either disintegration per minute or counts per minute or Curie, whatever you are taking unit is per unit mass in terms of moles or grams. So, you can say counts per minute per gram or per mole. So, that is a specific activity you take. An alternative method of expressing specific activity not so frequently used is atom percent excess, which is defined as number of radioactive atoms per total of 100 atoms of the compound. So, but that is not so frequently used. So, what you have is, one thing is that you have, if you want to do absolute counting, you have to convert counts per minute into disintegration per minute. Then you have to also consider about specific activity, as there is a stable carrier of in terms of stable isotope being mixed with the radioisotope. So, these are important things. Now, let us move on into rate of radioactive decay. Now, rate of radioactive, like we have seen what are the units being used, how it is expressed in terms of energy. Now, let us get into that how do you measure rate of radioactive decay. Now, the emission is a very spontaneous process, like I said earlier. Its decay occurs because of the processes which are confined to the nucleus of unstable atom and without any physical interaction from outside the atom. So, this is a spontaneous process. Another important part is that it is a random process. Radioactive decay is a random process at a single atom level. What does that mean? It means that as per quantum theory, it is not possible to predict when a particular nuclei will decay, and the decay of a particular nucleus will not in any way affect the time of decay of other nucleus. So, it is a completely random process, and it is not possible to predict when an atom is going to be decayed. However, the chance that a particular atom will decay is constant over time. So, this decay rate for a collection of large number of atoms is predictable, and it can be calculated from the measured decay constant of the nuclide. So, this could be done for a group of atoms or large number of atoms, but not for individual atoms. Now, let us understand this. the number of atoms of radioactive material disintegrating per unit time is proportional to the number of atoms of the isotope present at that time. So, if you have n number of isotopes present at a particular time, then the rate of disintegration will be proportional to that number, and it will, like as you go along, it will depend on number of radioisotopes present at that particular moment. So, what does that means? For a given sample of a particular radioisotope, the number of decay events will be expected to occur in a small interval of time, and they will be proportional to the number of atoms present. That is, if you can see here, that is the d n upon d t is proportional to n, that is original number of radioisotopes present at that time. Now, this could be converted to d n upon d t lambda n, where this particular quantity is known as decay constant, and it is a characteristic of a given isotope and is defined as fraction of isotopes decaying in unit time. So, the rate of change of the number of radioactive atoms is proportional to the number of atoms present multiplied by the decay constant. All right. Now, this decay constant is a characteristic of each of the radioisotopes. Now, if you can integrate here and convert it into logarithm form, then n t upon n 0, which means n t is the number of radioactive atoms present at time t, and n 0 is number of radioactive atoms originally present, is equal to lambda t. Now, it is much more easier now here to express the decay constants in terms of half life. We will see what is half life and we will discuss that. Now, half life will be defined as the time required for the activity or radioactive decay to decrease by 1/2. So, if n in the previous equation is equal to 1/2 of n 0, then t will be equal to the half life of the isotope, and as shown here in this, that you have taken the logarithmic value, and then finally what you get is t half, that is 0.693 upon lambda, which is the radioactive decay constant. So, what you can get is that you have a particular you can express the rate of radioactive decay in terms of half life, that is that how much time does it take to decrease by 1/2 of the original value, and we will see it is an exponential quantity, that is there is a exponential decrease here. Now, values of t half can vary widely from almost like 10 raised to power 19 years for say lead 204 to 3 into 10 raised to power minus 7 seconds for polonium. So, it could be very large or it could be very, very small actually. All right. Let us little bit discuss about half life. So, half life is abbreviated as t half, and half life is the period of time it takes for the amount of a particular substance undergoing decay to decrease by half. Now, half lives are used to describe quantities undergoing exponential decay. For example, radioactive decay, where the half life is constant over the whole life at the decay. Now, it is a characteristic unit for the exponential decay equation, like I told you, and it is expressed in that form. Now, if you see this figure here, this demonstrates the exponential nature of the radioactive decay. Now, here if you see, there are number of half lives given here, like half life 1, which is at 50%, half life 2, which will be 25%, because original value becomes 50. So, it is now 25%, and half life 3 will come what? It will be 12.5%, because it is half of the 25, and likewise you can keep on going. So, a particular radioisotopes decays in terms of half life as we calculate the rate of decay actually, and it is the exponential nature of radioactive decay. So, you can calculate from the original event that how many half lives particular radioisotopes have gone through. All right, this table gives you half lives of some isotopes which are used frequently in biological study. For example, 3H has half life of almost 12.46 years. Now, 14C has very long half life of 5760 years approximately. Na22, which has half life of 2.58 years, 32P is 14.2 days. So, this is very much suitable for many biological works like in field of molecular biology. Then 35S has 87.2 days of half life, 42K has 12.40 hours of half life, and likewise you can go on, like I-131 has 8 days of half life and I-135 has 9.7 hours of half life. Now, this is very significant because you would, when you are utilizing these radioisotopes for different application, like say in biological research or biotechnology research, then if it is a too long a half life, it is very difficult in storage and discarding this and also utilization. But if you have a like half life as 32P 14 days, this becomes very important and it becomes quite good for being used in biological research, because you can after certain period the this particular will decay its many half lives actually. So, this is very important. Half life is a very important phenomenon in radioisotope technique. Now, let us move on to how does this radioactivity interacts with matter. That is a very important part, because that is how detection will be done, and that is how you will understand that why certain certain emissions like certain radioisotopes with particular emissions are not used and some are used. Like I said, alpha particle emitters are not so much used and beta emitters are frequently used. So, let us go one by one. Now, alpha particles, they are relatively heavy. If you remember, if you can recall, they were like doubly positively charged with atomic number 2 and mass number 4. So, they will be certainly relatively slow. Beta particles, they are lighter and they are much lighter. They can be negatively or positively charged, and they will be faster than the alpha particle. Likewise, gamma rays, which does not carry any mass or charge, will be highly penetrating in nature. All right, let us discuss each of them. How do they interact with the matter and what are the consequences in terms of their application and toxicity. Now, alpha particles with considerable energy, with all particles of a particular isotope having same amount of energy, these particles interact with matter by causing either excitation or ionization. Now, excitation means energy is transferred from alpha particle to orbital electrons of neighboring atom, and the electrons being elevated to higher orbital, and then when they come back to the original orbital, then radiation will be emitted. Now, alpha particle will continue on its path with reduced energy, as it has transferred some of the energy to the electron, and the excited electron falls back to original orbital, emitting energy as photons of light in visible or near visible range. In ionization, here target orbital electron is ejected completely and the atom becomes ionized, that is, you get a pair which is positively charged ion and negatively charged electron. So, that is ionization. So, it could be either excitation or ionization. Now, as I said, because of their size, slow movement and double positive charge, they interact strongly with matter, because as they enter the matter and they are larger in size and slow, they are bound to interact more with the atoms which are coming in their way. And what happens is, as they interact more, they will produce large number of ions per unit length of their path, and their energy is therefore will be rapidly dissipated, and so what does that mean is they will not be highly penetrating. They are very slow, they are large, they do interact with matter, and so they will be not so much penetrating. For example, if you consider a 5 million electron volt alpha particle, it will only travel about 3.6 centimeter in air, and it is not able to penetrate even an ordinary piece of paper. So, that is how alpha particle interacts. Now, they can interact with either nuclei or orbital electrons. Now, when passing in the vicinity of nucleus, it may be deflected with no change in energy, which is called Rutherford scattering, or deflect with small change in energy, or absorbed by nucleus causing nuclear transformation. So, a lot of things could happen. Now, the most probable process involved in the absorption of alpha particle, however, are ionization and excitation of orbital electrons. Now, since alpha particles are low in penetration ability, they are usually not hazardous for external exposure. Like I said, it is hard, they cannot enter even a piece of paper, thin paper, but if the alpha emitting nuclide is deposited in on organism, then it is toxic. So, when internally deposited, alpha particles are often more damaging than most other types of particles, because comparatively large amounts of energies are deposited within a very small volume of tissue. So, they will be quite toxic and damaging for the tissues. So, in summary, alpha particles, they are slow, they are large, and they are not very penetrating, dissipating their energy very fast, and they could be toxic in certain cases. Now, let us see about how a beta particle, we are not going to discuss about positron. Like I said, it has a transient survival, it like annihilates very fast, but we will be discussing about the negatron or beta particle which is negatively charged. Now, these beta particles are small and rapidly moving particles compared to alpha particles. They are small and much lighter, they carry a single negative charge, and they interact with matter by causing either excitation or ionization. Now, beta particles can interact with electrons as well as nuclei. Beta particles passing near nucleus will be deflected by the Coulomb forces, and loss of the particle's kinetic energy may or may not occur. Coulomb's repulsion between the beta particle and electrons frequently results in ionization. Now, in the ionization process, the beta particles lose an amount of energy equal to the kinetic energy of the electron plus the energy used to free it from the atom. So, ionization will certainly, beta particles in ionization process will lose the energy. Now, beta particles may also cause excitation of external orbital electrons, as we have seen in case of alpha particle. So, what happens then, which in turn leads to the emission of sometimes UV photons. Now, like alpha particle, beta particles have a characteristic average travelling distance through matter, and that is dependent upon their initial kinetic energy. Now, beta particle with energy about 2 million electron volt will travel up to almost 9 meter in air and about 10 millimeter in water. So, comparatively beta particles will have higher penetrating power as they are light, and before dissipating their energy they will move to rather more distance as compared to alpha particle. Now, gamma rays, let us come to third one, that is electromagnetic radiation, which is gamma rays. Now, these are electromagnetic radiation, like I said, and have no charge or mass. They rarely collide with neighboring atoms and they are highly penetrating. Now, their interaction of photons or with matter involves several distinct processes, and we will discuss each of them one by one. Now, the relative importance and efficiency of each process is strongly dependent upon the energy of the photons, and there, like we will see, there are low energy, medium energy and high energy gamma photons, and also it will depend upon the density and atomic number of the absorbing medium. Now, three of the methods which lead to the production of secondary electrons, which in turn can cause excitation and ionization. So, gamma rays by itself is not ionizing or involved in excitation, but through electrons, secondary electrons which will be generated, as we will discuss, it is involved in excitation and ionization. Now, there is one called Rayleigh scattering. In Rayleigh scattering, when a photon interacts with atom, it may or may not impart some energy to it. The photon may be deflected with no energy transfer, it is elastic interaction, and this process is called Rayleigh scattering. So, this is not that important here, but the other three which we are going to discuss will show you how they will interact and cause different phenomena. One is photoelectric absorption. In photoelectric absorption, low energy gamma rays will interact with orbital electron. Now, in this process, the photon transfers all of its energy to the electron and its own existence terminates. So, the electron will escape its orbit with a kinetic energy equal to the difference between the photon energy and its own binding energy, and will behave like negatron, and as we have discussed, it will behave and do all things as negatron. So, what is happening here, that there is a low energy gamma ray interact with electrons and will transfer its complete energy, and its particular existence will not be there anymore, and then that orbital electron will be ejected and behave as negatron. Now, let us see how does it, this figure shows that particular phenomenon here, that there is a gamma ray coming, it will eject this electron from here, transfer its whole energy, and the electron is ejected as a photo electron in this case. So, low energy gamma ray will have a particular way of interacting. Now, let us see the medium energy gamma ray. Now, here it is, this particular effect is called Compton effect. In this process, the photon interacts with an atomic electron sufficiently to eject it from orbit. The photon retains a portion of its original energy. Remember, this is a medium energy and not a low energy photon, and it will continuously it will move continuously in a new direction, because it will be deflected actually. Thus, the Compton effect has an absorption component as well as scattering component. The amount of energy lost by the photon can be related to the angle at which the scattered photon travels relative to the original direction of travel. So, here in the Compton effect, you have energy partly transferred for ejection of electron or negatron, and partly some energy is carried, or it is carried over as a low energy gamma ray. Let us see, try to understand this in figure. So, what happens, that you have a gamma photon with medium energy, it hits orbital electron, electron is ejected, and the gamma ray continues in a new direction here. So, and this again can act as a low energy photon here. Now, third one is pair production. Now, this pair production occurs when there is high energy gamma rays. So, what happens, high energy gamma rays interact with nucleus of an atom, and all the energy of the gamma ray is converted to positron and negatron. So, remember here, rather than ejecting a simple electron, orbital electron, here it is interacting with nucleus of an atom, and its all energy will be converted to positron and negatron. Now, photons with energy greater than 1.024 million electron volt under the influence of the electromagnetic field of a nucleus may be converted into electron and positron. Now, at least this much of energy of photons are required for a pair production, and because it is equivalent to 0.51 million electron volt each, and then pair production will occur. If you can see here in this figure, there is an incident photon which is high energy photon. In influence of atomic nuclei, it is converted to positively charged and negatively charged particles, which is negatron and positron. So, this is like only happens with the it only happens with the high energy gamma rays. Also there are a whole lot of different things which will be interacting. Neutrons can interact and encounter biological material. It is utilized in for a lot of biological applications, and it will collide with a proton with a sufficient force to dislodge the proton from the molecule. Proton may then have sufficient energy to travel some distance in the tissue, causing secondary damage through ionization and excitation. We are not going into detail of that, but this is also an important particle which could be utilized or which can interact with matter, and it is utilized in like say neutron diffraction and lot of other techniques here. This figure here summarizes the interaction of gamma rays with the matter. Now, if you can see here, this is like atomic number and the x axis gives you photon energy. Now, if you can see in different areas are distributed in here. So, there is a low energy area which have dominant photoelectric effect. What does that mean? That low energy gamma rays will show photoelectric effect. The medium energy gamma rays will show Compton effect dominantly, and the high energy gamma rays will show the pair production here. So, you have three kinds of effects of gamma radiation which are shown in here and summarizes the whole interaction very well. All right. So, in this lecture what we have summarized is many different basic concepts. One is that how the in terms of energy the radioactive decay is measured, which we have said it is in terms of electron volt, or which is million or mega electron volt, which is larger unit, because electron volt is a very small unit. We have seen what are the units of radioactivity, which is expressed in terms of becquerel, which is gigabecquerel or terabecquerel, and also it is widely used in terms of Curie, where you use microcurie or millicurie. We have seen that the energy of we have seen about the beta spectrum. In alpha and gamma there is a range of energy of radioactive decay, but the beta emitters they emit radiation in a wide range from 0 to to a maximum value for each of a typical radioisotope or beta emitter. We have seen the interaction of the different radioactivity with matter, as we have seen that you have alpha particle, which is a heavier particle, which is doubly positively charged and slow. It interacts rapidly, it interacts quite a lot with the matter as it enters the matter, and will dissipate its energy very fast and will cause ionization or excitation. Like I said, it is quite toxic if ingested, because it will cause too much effect in a very small area and can create tissue damage and other problems. The beta particles are slow entities and they are faster than the alpha particle, and they are the ones which are used most in biological work of different energies, like it could be low energy beta particle emitter, or medium energy beta emitters, or high energy beta emitters, and we will discuss them as we go along. Then there is electromagnetic radiation, gamma radiation, which in itself does not carry any mass or charge, but it also causes ionization or excitation through the beta particles, which with the production of which takes place through various effects which we have discussed, like photoelectric effect, Compton effect, or pair production. So, this completes our here the basic concepts which we were discussing. Now, we will move on to the particular methods of detection and quantification in the next lecture. Now, three methods which we are going to discuss one by one, based on the gas ionization, where the GM counters have been developed to detect the radioactivity, and we will see what are different types of these counters and how they are useful. Then we will be discussing about the methods based on excitation. So, one is ionization, like if you could recall, we have told you both beta particles or alpha particles in gamma radiation can cause both ionization and excitation. So, on methods based on excitation will be discussed, where scintillation counters have been developed, and we will be discussing them in detail. Then another one, third important method is autoradiography, that is exposure of radioactivity to photographic film, that we are going to discuss in subsequent lectures. So, this we complete here. Thank you.